All right, so what is the secret sauce that gives quantum computers their almost magical power? Well, what if I told you it's a kind of connection, a bond in the universe so deep, so instantaneous, it's like a secret chord playing behind the scenes. Today, we're going to tune into that chord. We're talking about quantum entanglement.
So where do you even begin with something this weird? Well, it turns out the best place to start is with the guy who was most famously freaked out by it. We're talking about a cosmic mystery that deeply bothered Albert Einstein himself, and he even gave it a nickname that stuck.
Yep, that's the one. Spooky action at a distance. I mean, it sounds like something out of a ghost story, right? Something impossible. But here's the kicker. It's absolutely real. I mean, just try to wrap your head around this. What if you could take two particles, two tiny bits of the universe, and link them? Link them so perfectly that they're basically one system forever. You look at one and you instantly know something about the other, even if it's light years away. Okay, let's use an analogy. Think about flipping a regular coin. The outcome is random, right? If you flip another coin, its outcome has absolutely nothing to do with the first one. They're two separate events. But now, imagine you have a pair of charmed coins. You flip one and bam, it's heads. Instantly, without even looking, you know for a fact that its partner, wherever it might be, just landed on tails every single time. Their destinies are connected. That's the feeling of entanglement.
Okay, so it's time to give this spooky connection its proper name and figure out the rules of this strange cosmic dance. We're calling it the Entanglement Waltz. And of course, to help us out, we're going to need our trusty guides, Alice and Bob.
So, formally, what is quantum entanglement? It's when two or more particles get linked up in such a way that they essentially share the same fate. Think of it like a pair of magic dice. You give one to Alice, one to Bob, and they go to opposite ends of the earth. If Alice rolls hers and gets a 6, she knows instantly that Bob's die must be a 1. Their total is always 7. It's a perfect correlation, no matter how far apart they are.
And this right here, this is why entanglement is such a game changer for computing. See, a normal computer bit is like a soloist. It can play one note at a time, either a 0 or a 1. That's it. But entangled qubits, they're like a band. The magic isn't in what one qubit is doing, it's in the harmony they create together. It's the relationship that holds the information, and that lets you create much, much richer music. Or, in this case, calculations.
Okay, so that all sounds cool, but how do we get from a neat physics trick to the actual engine of a quantum computer? How do we unlock all that power?
Well, let's look at a famously hard problem, the traveling salesman problem. All you're trying to do is find the shortest possible route to visit a handful of cities. Sounds simple, right? Well, with just 10 cities, there are over 3.6 million possible routes. A classical computer has to check them one by one by one. It's just a long, slow grind.
But a quantum computer is different. Because its qubits are entangled, they can share notes with each other about the problem. This lets the computer look at a huge number of those 3.6 million routes all at the same time. It's not checking them one by one, it's exploring the entire landscape of possibilities at once to find the shortest path way, way faster.
So this gives us some serious superpowers. You get this massive parallel processing, right? The ability to probe tons of solutions at once. You also get richer information because the data isn't just in the zeros and ones, it's stored in the connections between the qubits. And, this is the essential fuel for some really powerful quantum algorithms, like the famous codebreaker, Shor's algorithm.
Okay, this is all fantastic in theory, but how do you actually make it happen? Is entanglement just something that randomly occurs in the universe that we have to hope we can find and harness? Nope. The amazing thing is we can engineer it. We can build it on purpose in a lab. It's almost like brewing a potion, and the key ingredient is something called a C0 gate. Here's the recipe. Step 1, you take 2 qubits. We'll call one the control and the other the target. Step 2, you put that control qubit into superposition so it's in that fuzzy state of being both 0 and 1 at the same time. And now for step 3, the magic part. You apply the C0 gate. And all it does is follow one simple rule. If the control qubit is a 1, it flips the target qubit. That's it. That one tiny conditional rule is enough to link their fates forever. Voila! You've just created entanglement.
So let's kind of pull back and look at the big picture here.
We started with something spooky, but maybe a better way to think about it is as a powerful, elegant duet happening on a cosmic scale.
But before we wrap up, we gotta set the record straight on a couple of common myths. First, this does not mean we can send instant messages across the galaxy. It's a correlation, not communication. You can't use it to send Morse code faster than light. The other big one, that more entanglement is always better? Also not true. Sometimes too much of it just creates noise. You need the right kind and the right amount of entanglement for the specific problem you're solving.
So in the end, it really is like a cosmic duet. The true information, the real power, sings through the relationship between the qubits, not just in their individual notes. And the incredible part is that we are learning how to be the composers, using things like C-Not gates to write the music for this incredible symphony, and using it to solve problems we never thought were possible.
And that brings us to a final, really fascinating question. If a quantum computer is using superposition and entanglement to explore all those millions of routes at the same time, how in the world does it pick out the one right answer from all that noise? Think about that for a second. The answer? Well, that's where another quantum superpower comes in, something called interference. And that's exactly what we'll be tackling in our next explainer.